So resonance is when more than one dot diagram is possible, but the atoms are in the same order. So there's more than one dot diagram, but the only difference is electrons. So the atoms are in the same place, but the electrons are in different places. And the way that happens is you get to a point where you have a choice for a double bond. Get to a spot where you have a choice for a double bond. Okay? You do the math, you figure out you need a double bond, and you've got your choice about where it goes. Okay? And where it goes doesn't matter. So what do you mean where it goes doesn't matter? Well, let's draw the electron dot diagrams for nitrite. It's a polyatomic ion, NO2 with a minus charge. Because it's got a charge, we have to do the math. Okay? There's no way around it. Because something's going to have the wrong number of bonds because they had to put another electron in to make this work. So we don't know which one's going to have the wrong number of bonds. So happy for one nitrogen is 8. For 2 oxygens is 16. So a happy number is 24. Have for one nitrogen is 5. For each oxygen is 6 times 2, that's 12. And then the negative 1 means I have to add another electron, because the way I get a negative charge is by taking an electron. And 5 plus 12 is 17, and 1 more is 18. 24 minus 18 equals 6 divided by 2 equals 3. So I have to put in 3 bonds. And now I have a choice about where the double bond goes. I can write the double bond here, or I can write the double bond there. I have my choice about which side. Okay? And I'd have to fill those up. The double bonded oxygen needs 2 more pair. The nitrogen needs 1 pair. The single bonded needs 3 pair. Oops, that's too many on the nitrogen. And if you count the dots on either one, you're going to find 2, 4, 6, 8, 10, 12, 14, 16, 18. Our half number. Okay. So I had my choice about where to put the double bond. It didn't affect anything. The only difference is that the double bond's here or there. So what happens is I bring one of these pair down to make a lone pair. That's going to push this one off because it can't have another pair. You got a lone pair over there. So these electrons come down, make that bond, kick that bond off, and put a pair over there, and I end up with the first one. So there's more than one way to write this. Which one is it? Does it actually go back and forth? We can see that those electrons hopping would move that double bond from one side to the other. Well, originally, they thought it went back and forth. They thought that's what happened. That some of the times you had a double bond here, and sometimes you had a double bond on the other side. And since it can go back and forth, going back and forth, flipping back and forth, is called resonating. So they called this thing resonance. The fact that they thought this could flip back and forth. Okay. But they knew something. They knew that double bonds are shorter than single bonds. So if NO2 had one double bond and one single bond, it would have one long bond and one short bond. No matter which one I drew, there'd always be one long and one short. But when they measured the length of the bonds, they were all the same length. They were both the same length. They were longer than a single bond, or sorry, shorter than a single bond, but longer than a double bond. They were in between sizes, but they were the same size. So instead of a long one and a short one, we had two medium-sized ones. Two middle size. Okay. So that told them that the problem was in the way they were drawing things. That instead of one bond and two bond, it's really 1.5 bonds and 1.5 bonds. It's really in between the two. Like a mule ends up in between the size of a horse and a donkey. Right? So you end up with a blend of those two, someplace in between. They're all on YouTube. If you, I mean, all you do is they're the same length. That's what it said. The bonds are the same length. Okay? So the actual one, the problem is we don't want to draw this or the other one. What I really want to draw is 1.5 bonds. But the problem comes when you draw 1.5 bonds, try to fill in the rest of the dots. Do you see a problem when you try to fill in the rest of the dots? And that's what it is. The problem is with our method of showing things. It's not a problem with what nature does. Instead of getting one long one and one short one, you get two middle-sized ones. Okay? Nature doesn't have a problem with that. Our problem is we can't draw it well. It's a problem in our model. Our bookkeeping doesn't work real well. So what do you do about it? Well, you draw both pictures. And then you put a double-headed arrow in between to say it's really in between these two. So let's look at another place it happens. Carbonate ion. Yeah.
So are they both considered different isomers of each other?
No, it's actually two different pictures trying to show one kind of molecule. The real one is someplace in between those two pictures. So it's the same chemical drawn with different electron arrangements. So the real one is someplace in between.
You draw with a double arrow.
In between the two of them, yeah. Yeah. So we'll go through that whole process here with carbonate. Okay. It's got a charge. If it's got a charge, I have to do the math because there's 2 extra electrons. I don't know where they're at. Okay. That's how you get a 2- charge, is getting 2 extra electrons. So my happy number for 1 carbon is 8. For 3 oxygens is 3 times 8 is 24. So my happy number is 32. Okay, with that, I got 32. Yep. Have. I write have. The carbon has 4. Each oxygen has 6, and there's 3 of them. So that's 18. And that 2- charge means I have to add 2 more. That the charge affects my have number. That's 20 and 4 is 24. 32 minus 24 divided by 2 is 8 divided by 2, which is 4. So this has to have 4 bonds. Okay. Well, which one's going to go in the middle? Well, the one that wants to make 4 bonds. Actually, if you see anything that's written like this, where it has an element and a whole bunch of O's, the oxygens all surround that middle one. Because oxygen can come in and make coordinate covalent bonds because it's got 2 missing, so it can fit on any pair of electrons for any molecule. So you can add those O's pretty easily. So we got a C, and it's hooked to 3 O's. Here's my 3 of my bonds. Where does the 4th bond go? Does it go here? Or does it go here? Or does it go there? I have 3 choices where the double bond goes. I have to draw them all. Okay. Then I have to fill everything in. The carbon's full. The double bonded oxygen needs 2 more pair. The single bonded oxygens need 3 more pair. Oops, I forgot this one over here. Make sure everybody looks like a noble gas. Now, all of those have 24 dots. There are 24 dots on all of them. Now, I don't know if you remember this, but there's 2 extra electrons in here, and we had a way of saying extra electrons. We took and put brackets around it. That has some extra electrons. So does this one, right? This has some extra electrons. And this one has some extra electrons. So I put the charge outside. We talked about that earlier. We haven't run into it, but you put the charge outside. And then you put double-headed arrows in between, saying the real one is someplace in the middle of this. Instead of a double bond and 2 single bonds, it's really 1 1/3 bonds distributed all the way around. We just can't draw 1 1/3 bonds. So the reason why we have to draw 3 pictures is because it was a problem with our model, not a problem with nature. Nature doesn't have problems making 1 1/3 bonds. We just have problems drawing it. It's a flaw in our model. There are other models that deal with it better. We're just not learning them this year. So when we have a choice about where to put double bonds and it doesn't affect the atoms at all, we draw them all in the places they can show up. Okay? Whereas yesterday, when you put a double bond in, you had to move atoms around, right? Those were isomers, completely different chemicals. Resonance, different pictures where the real one is the average of all those. Isomers, same formula but completely different chemicals. Okay. So resonance. Let's try one last one, N2O. Actually, this is one that causes a lot of grief the first time we did it. Remember where we had N2O and the end was central? And we had all these extra bonds we were trying to draw? Okay. I'm going to do the math here because I can't picture how it's going to go together. So I got 2 N's and 1 O. I worry about what I happy and what I have. Nitrogen is happy with 8, and there's 2 of them. Oxygen is happy with 8. So that's 3 8s, and 3 8s is 24. Nitrogen has 5, and there's 2 of them. Oxygen has 6, so 10 and 6 is 16. 24 minus 16 is 8. Divide by 2. I have to put in 4 bonds. I've got 3 atoms, but I have to put in 4 bonds. Hydrogen is the only one that's happy with 2. Yeah. So it looks like helium. Okay. So I got N hooked to N, hooked to O. There's 2 bonds. I have to put in 2 more. And there's 3 possibilities. I could make it 2 double bonds. Or I could make it a triple bond and a single bond. or I could make it a single bond and a triple bond. Right, I got 4 bonds. Those are the possibilities. Okay. So before we move on, one of these won't show up. 2 of them will, 1 of them won't. Okay. The first one will because oxygen has the right number of bonds. Ever see how oxygen has the right number of bonds there? The second one will because nitrogen has the right number of bonds. On this last one, nothing has the right number of bonds. Okay? So we don't expect to see that one when there's ways to make it where you can make the right number of bonds. Okay? So this one doesn't show up because it doesn't make the right number of bonds. Fill in all the dots. That one gets 2 pair and that one gets 2 pair. Nitrogen gets 1 pair, the oxygen gets 3 pair. And in both of those pictures, I've got 2, 4, 6, 8, 10, 12, 14, 16, which was my half number. Do I need brackets this time? Brackets are about charge. Does this have a charge? Nope. Okay, all I need is a double-headed arrow. So if they ask you to draw the resonance forms, okay, and that's the only time you really have to do it is when they ask you to do it, because it doesn't affect anything else about them, just about how you draw them. It doesn't affect how they behave. If it asks you to draw resonance forms, you have choices about where to put the extra bonds. Show it in all those places. Okay. What's special about resonance? The more resonance structures it can make, the more stable the chemical is. So things that can make multiple resonance structures are more stable. They're more stable because there's more ways to have low energy. That's what we're trying to get to low energy. The lowest energy. So lots of polyatomic ions have lots of O's around it because the more O's they can fit on, the more resonance structures they have, the more stable they are. Yeah. The book's example was ozone, right? O3. If you read about ozone in the newspaper, it shows up daily in the smog report. Ozone is a pollutant in our area. But when you go up to the upper atmosphere, it happens to absorb ultraviolet rays. It's got the right energy to absorb ultraviolet rays. So it blocks ultraviolet so we don't get cancer. So close to the Earth, it's bad for us. Way up in the atmosphere, it's good for us. Because for years, there was a lack of ozone above Australia, and they had to slather on the sunscreen because there was nothing stopping the UV. Okay, how does ozone form? Well, we know oxygen wants to make 2 bonds, right? So O2, we'd expect to look like this. Right, that's O2. And then oxygen, a third oxygen, can come in and make that coordinate covalent bond. Right? It's 6. Both electrons came from here, and it could do it to either end. So it could have done it to that end as well. So another way of drawing this would be with the double-headed arrows, or with the arrow to say it was a. So that's how ozone forms, and there's the 2 forms of it. Okay. Oh, I posted it, and I forgot to write it on the board. It's where'd it go? It's page 225. I didn't even have a pen to write with. Oh, page 220. It's on School Loop. Page 225, 10 through 12.